And we are live, I assume. So, hello everyone and welcome. Today I want to talk about something that appears in almost every modern architecture, but it's still often treated like something generic, which is encryption in transit. So more specifically, I want to focus on what certificates actually do, why TLS is about more than just encryption, and why mutual TLS matters, and uh, uh, um, and how services can trust each other when they need to trust each other across the system, platforms, and different cloud vendors. When I say that people are taking sometimes this as a generic, like you hear almost if you are doing this job, you hear every day something like, yeah, services needs to be encrypted in transit. That is the requirement. You hear the terms like TLS, maybe SSL, or something similar, but or public or private keys, exchanging keys and stuff. But if you if you are interested to find out what is happening under the hood and why that is important, then this webinar is exactly for you. So the goal today is not to turn this into some kind of cryptographic lecture. The goal is to make this trust model intuitive and practical. And before we dive in, of course, a quick note about who we are. So here at Serverless Guru, formerly Serverless Guru, now we are SLS Guru, we spend a lot of time helping teams design secure and practical architecture, and the topic comes up constantly. That topic comes up constantly whenever services need to communicate safely at scale. So what I want to share today is not just a theory, it's a practical way to think about trust between the systems. My name is Almir Zulic. I am a principal dev at SLS Guru, and I'm going to guide you through this presentation in the next 30 minutes, if my dog allows me, but hopefully it will. So here is our plan, our agenda for today. So first, I will explain why encryption alone is not enough. Then we will define what certificates really prove, why certificate authorities exist, what they are, how TLS uses the trust model during the handshake. Yes, that's a word, and that's how it is called when services establishing connection. From there, we will move into mTLS. There is a small m there. When it is the right choice, how public and private certificates authorities differ, and what a practical cloud implementation looks like. Then we will close with common mistakes, key takeaways, and a short walkthrough. Of course, you have a production-ready source code on the GitHub. I will share the link at the end presentation, but you can also find it in the article. Link will also be shared. If you are following SLS Guru on social networks or on LinkedIn, you can find the latest article there with the links to this webinar and to the source code itself, which is inside the article. So let's start with the actual problem. So what we are solving here, what's the problem? In modern systems, services constantly exchange sensitive data across networks. The usual requirements say something like use encryption in transit, as I said in the at the very beginning. So lots of big words. It sounds good. Yeah, we are going to have encryption in transit, but it's only half of the story. Encryption alone protects confidentiality. It helps prevents eavesdropper from reading the data. So what is the eavesdropper? That's something or somebody who is trying to steal our data, who is trying to follow our conversation and get the information that we do not want to share, which are actually the secret. So we want to keep our communication private. So that is the real problem we are solving. It's not, we do not just need secrecy. We need secrecy and identity, and you will see why. So we need to know that the service we are talking to is the service that it claims to be. This is this diagram will hopefully shed a little light on it. So this is where man-in-the-middle attacks and service impersonation become important. They are not they are not important. It is important to prevent them. So what is the man in the middle, and why identity is important? So when you are communicating somebody on the distance, like you're using some kind of chat or messenger or whatever, you are exchanging messages, and that's fine. Your messages are encrypted in transit, and nobody can read them because they are encrypted. That's fine. But how do you know that the person that you are chatting with is the actually person that it claims to be, so that they are not impersonating somebody? This is what we are. This is what we are trying to solve. Because what is the man in the middle? What is the man in the middle attack, and what is the service impersonation? So man in the middle can, if attacker is successful, it can listen to our conversation and be able to decrypt somehow, or even to listen conversation before it is encrypted. And the service impersonation, of course, is that the service is impersonating to be something else, something the service that we are actually want to call, instead of malicious service or attacker service put there to get our data. So this diagram shows how it's supposed to be, and it shows what happens in the situation that we want to avoid. So this is something very specific. When I say we need to trust somebody, when I mention the word trust, and it will be mentioned a lot in this talk, I mean something very specific. So not just that the traffic is crumbled, but both parties can verify who they are really communicating with before the real data starts flowing. And this is also important concept. You will see the difference between asymmetric keys and asymmetric encryption and symmetric encryption. Hopefully, I will explain that in a plain terms and how that is used. So let's start first with the certificates, what they really are, and the best way to understand this is like a digital identity document. So we all do have, hopefully, identity cards which proves our identity in front of some kind of authority. So you have, if you are traveling a lot, you probably have a passport. The digital, you can think about the certificate, about the digital identity document for services, devices, users, or domains. And that identity binds to a public key. So the part alone is not enough. I can just take a piece of paper and put here and stick here and say, yeah, my name is, I don't know, Almir. Yeah, that's me. But how can I prove that? So we need some authority to prove that. So if I may be impersonating Almir, maybe I'm not the real person. So somebody needs to verify my identity and confirm that I'm the person who I'm claiming to be. The same thing goes with the certificates that are binded to a public key. So they need to give you the identity of that digital service, or whatever that is, device, user, domain, whatever. So the certificate turns a raw public key into something verifiable. It gives us a way to say the key belongs to a specific identity, and that statement was signed by a trusted issuer. So like having I don't know, border police or somebody who or regular police on the street who takes your ID and say, okay, yeah, that's the person. So without certificate authority, we are back to ad hoc trust. So if you don't have that control, if you don't have that official person or service, in this case, digital service, we are back to ad hoc trust. There is nobody who can tell me, yeah, that's the real service. So if we go ad hoc, that means that we would exchange keys and simply hope they really came from the party we intended to talk to. This is exactly the kind of gap that an attacker wants. This is the situation they want. So a certificate authority gives us a chain of trust. Instead of trusting every key manually, the client checks a few critical things. Was the certificate issued by a trusted authority? Is it still valid? Has it been revoked? And does the hostman or host name or identity match what the client expects? So I mentioned a couple of interesting terms here as revoking certificates and are they valid? So if somebody tampered with certificate, obviously, like if you are using JWT tokens, you know that if somebody tampers with the token, it's not valid anymore. So somebody needs to check the validity of this. Somebody needs to check validity of the certificate, and if something goes wrong, like with your passwords, if password has been compromised. Or if you are just regularly changing password as you should, then this is the same thing. So you should not let your certificate to live forever. So it needs to be rotated from time to time, and you need to be able to revoke certificates. If you are following recent news, you will see a lot of articles in the internet on the internet. Recently related to the usage of AI, missing code reviews and stuff, and even publishing these certificates, which allows people or devices and the services to impersonate to be something else. So when this validation happens early during connection setup, before the real application exchange the data between the two parties. So in practice, this is what blocks impersonation before it becomes a breach. When I say this, I mean this validation. So let's explain TLS in 60 seconds what that is. If you're not familiar with it, so it's a general purpose protocol that gives us encryption, integrity, and authentication. So most people associate TLS only with HTTPS. Yes, it is associated with HTTP because HTTP plus TLS gives us the HTTPS. But the same trust model you can find in many different places. It's not just for HTTPS. It is used in the SMTP. It's used on IMAP. It's used even in MQTT, or if you are using, and you probably do, if you are on this webinar, databases and you're establishing database connections, you will see TLS there as well. Basically, anything that needs secure communication over TCP use TLS. So the short version is like certificates are used during setup to establish identity and trust. And after the handshake, the actual data is protected with symmetric encryption because it's much faster. And I'm going to talk about symmetric and the asymmetric encryption in the upcoming slide. So that is why TLS is practical. It combines identity and secure transport in a way that is both. We need it to be trustworthy and we need to be efficient because nobody wants to wait for the data, right? So let's make this handshake concrete. So what is the handshake? Like people introducing to each other. That's where this name comes from. That's how services are introducing. That's how TLS introducing peers. There is a handshake, and the establishing connection starts with the client hello. It proposes protocol settings, supported options, and key agreement information. Again, lots of big words, but this is how client introduces itself to server. So server responds with server hello, yes, I'm here, and chooses the final parameter and sends its certificate. Now the critical trust step comes. So the client validates that certificate. It checks is that really issued by the certificate authority that the client trusts. Whether the certificate is valid or invalid or not encrypted, it should be rejected or even revoked. But if everything is fine, if it's valid, if it's not expired, if it's not revoked, and host name and identity match what the client intended to reach, then client considers, yeah, that's the server I want to talk to. So if that succeeds, the handshake continues with the key exchange. So both sides derive the same session secret, and then, just only then, traffic exchange starts. So the handshake is not just about turning encryption on. It is the trust establishment phase of the connection. Now, TLS uses both asymmetric and symmetric cryptography because each one solves a different problem. So asymmetric cryptography is excellent for identity and authentication and secure key agreement, but it is computationally heavy, especially as data grows. So when you it's not very well suited for the data exchange. In practice, the data that you encrypt should not exceed or cannot exceed the size of the key, because behind all of this cryptography thing, there is a mathematical algorithm, and computing these keys is really really expensive operation for your CPU, and that will not be very efficient to use for each package you are sending over the network. So what you do with asymmetric keys, you establish authentication and identity, and then peers securely exchange symmetric key, because symmetric key is the opposite of the asymmetric. So it's very fast and efficient for the traffic. So if you're wondering why we cannot just use symmetric key, well, that's the problem. That's the issue TLS is resolving here. Because how do you know if you send me that secret key that somebody will not intercept that in a transit, and if they get this key, they can decrypt data the same way you are decrypting. So this is the secure way that you exchange that symmetric key. And once the server and the client or peers does have the same symmetric key, then they can exchange data securely. One will encrypt data and send it over to another end, and they will be decrypted, and the response will be encrypted again and sent back, and that peer will be able to decrypt message. So TLS combines both. Certificates and private keys establish identity and trust. The handshake derives a shared session key. That's how this symmetric key is called. And then the session key protects the actual traffic, and at very good speed. It's much faster than using asymmetric. We already said why it's not very well suited. So at this point, it's worth addressing the obvious future-looking question: what happens in the quantum era? So why am I mentioning this? So a lot of today's public key cryptography uses RSA algorithm, and that is perfectly fine. However, the problem that arises here is that there is a math algorithm very well known since I think 1994. It's called Shor's algorithm, and that is the algorithm that derives private key from the public key. So it is possible from the public key to extract private key. However, there is a catch. There is no supercomputer currently in the world. There are no resources in the world that they can decrypt RSA in a meaningful time. So you will need millions of years to decrypt it. And then there is another catch. As the quantum computers are evolving, they will be able to do this in seconds or a minute. So that is the future problem, but the solutions are being built now in advance before the quantum era. If you look into this screenshot from the AWS certificate authority, you will see that you can choose post quantum era. So why this is important? Keep in mind that the long-term data can be compromised in the future. Will that be in the 5 or 10 years? Doesn't matter. Long-term data are long-term data. For some data that are relevant today are not relevant tomorrow, it's not an issue. But if there are long-term secrets that needs to stay secret, they would need to be encrypted with something else. Why? Because when the data there is a well-known attack called harvest now, decrypt later, and that explains everything. So the attacker can patiently collect, harvest the data from the everyday communication. For example, your Bitcoin wallet. If you share public key, if you make a transaction, they can harvest the public keys, and in 10 to 15 years, they would be able to decrypt it and empty your wallet or whoever owns that. So that is the one of the upcoming issue. Not today, but for the future use, you should be aware of this. So for now, it's perfectly fine to use this hybrid approach. Use RSA for the handshake and use something as AES for the data exchange, which is a perfectly safe algorithm, even in the quantum era, if the key size is big enough. So what is this thing that is called mTLS, which we mentioned at the beginning? So that is the mutual TLS. So in standard TLS, the server usually proves its identity to the client. That answers the question, is this the real server? In mTLS, the client also presents a certificate. Usually TLS is enough, but in mTLS, both sides authenticates each other before application data is exchanged. So this is especially valuable in service-to-service communication, because in the backend system, the server also needs to know whether the client is really the service it trusts, not just whether the transport is encrypted, as mentioned. So simplest way to compare them is this. TLS gives you a trusted server and encrypted channel. mTLS gives you a trusted server, trusted client, and an encrypted channel. That additional client identity check is what makes mTLS so powerful in internal architectures, where one service needs to make security decision based on which other service is calling it. So the mental model is kind of, well, let's say simple. TLS answers, is this a real server? mTLS adds, is this the real client service too, as well? Because so why do we need mTLS? And when mTLS is the right choice, so why don't we just use TLS? So because there are some regulated environments, and you will you have a zero trust. So for some compliances, it must be end-to-end encrypted with the mutual identity. And in the demo that you will see, services are communicating with each other over the network across the different cloud vendors, and it's better that you are that you know to whom you are communicating with, instead of just trusting, yeah, that is the service. So it is a strong fit for a service-to-service communication inside the platform for zero trust or defense in depth architectures. So these are all security things and terms that if you are not very familiar with, you can Google it, because there are lots of very interesting articles and the books to learn from. Because security was never more. It was always probably the most important thing in these architectures, but probably today with the AI thing and the lack of reviews and people just trusting what AI produces, it became more important than ever. So let's talk about a little bit about the public and private certificate authorities. So public certificate authority is usually is something that you see every day. So those certificate authorities issue certificates for internet-facing domains. So when you type in your browser HTTPS google.com and you get that badge that the connection is secure, you can view certificate, you can see the certificates, and check the signature and see that it is actually from the trusted authority. So then you know that you can trust that website. Okay, they can always be malicious code on the website, intentionally or not, but at least you know that the site that you are communicating with does not impersonating something else. So nobody there is nobody there was tampering with the real website. Now these public certificate authorities cannot work in your private network, in your isolated network, because you don't want. There are services that needs to work within your VPC. If we are talking if we are talking in the AWS context, you don't want them to communicate with the internet. So external public certificate authority will not work. So that is where private certificate authority comes into the place. And another important and nice thing is that internally you can have your private DNS names. So you know, when you again, I will take AWS as an example. When you are developing services and you have API gateway, you get a generic domain name, which is very long and hard to remember. And you want to have something meaningful. You want to have your organization.local domain, for example. In our case, let's say it could be sls.guru.local. That we cannot use public certificate authority for that. We can use private certificate authority. So it is not just about authenticating. It is also enables you to have a private DNS. So, and you know, like the common mistake, and a lot of teams, I see this on a lot of places, not everywhere, of course, but I saw in a lot of places. Yeah, we don't need a secure connection because the network is isolated. Well, not really. So yes, your private network means it is a trusted network, but it only takes one compromised instance or one bad security group or one routing mistake and one misconfiguration or whatever you want to call it, and to turn that assumption into a problem. Because if attacker get access to your network and you don't have encrypted transport end to end, your data may be and probably will be compromised. So the rule of the thumb is simple: public CA for public certificate authority CA for public trust, and private CA for internal use. So from the implementation perspective, use managed services where possible. So you don't want to reinvent the wheel, and you don't want to create or develop these private certificate authorities. So on AWS you have private certificate authority service. I will show you how to create it, and you can configure these services not just on AWS, on other vendors as well. But in this case, you can configure private certificate authority to require and verify certificates, even if no matter what you're using, mTLS or TLS. So it's just are you doing one side or both side authentication. So and yeah, there is one important nuance. If you are using a private certificate authority, that the clients does not trust that authority by default, you will need to install root certificate from that authority on your client, because you need to establish trust first with that authority. You say, yeah, I trust that authority, and then only then you can and should use the certificate authority. And this is where actually the architecture from theory, this is where we are coming into the practice. So common mistakes to avoid that I already mentioned is that first assuming that private network is automatically trusted. No, it's not, and trust no one. That's the rule of the thumb in security. I'm sorry, but that's how it goes. The second is enabling TLS, but not validating identities correctly. So which means you have encryption without meaningful trust. And I already talked about that. So somebody can impersonate the service or a user or whatever on the other end, and you are encrypting data, but you are sending the data to somebody who can decrypt them, but not the one that you are expecting to be on the other end. So you should never expose your private keys. That's also, I mean, that's obvious, but private key is like your password. So another common mistake, not that often, but it happens that people treat mTLS like authorization. It's not authorization. It is authentication. So it just proves who is on the other side. So I know I mentioned this a couple of times, but it is really, really important to understand how this goes end to end. So first establish identity and then secure the transport. Then you apply authorization policy and least privilege principle, but that goes on the application level. That's not what mTLS and TLS are about, because this is how you prevent a false sense of security. You can make a checklist with this, and when you are implementing these services, and there are some best practices checklist available, but be aware that mTLS is not authorization, TLS is not authorization. So that's about the identity and the transport, and on application level, you do your least principal privilege, role base, and so on and so forth related to the authorization. So let's summarize the main points. Certificates are digital identities, like the person ID or passport. Sorry. Certificate authorities establish trust on scale. So TLS protects the channel and authenticates the server. mTLS extends that on the both end, so that the both sides authenticates to each other. And the most important takeaway is this: the real goal is not simply to encrypt the traffic. The real goal is to prove who is talking to whom. So the whole thing together makes the system secure, not just one without the second, or first without the second and the second without first. You need to implement all of this to have a secure system. So if your architecture get that part right, encryption in transit becomes really real, trustworthy security control, instead of just one more compliance thing that that you need to do. So since I took too much of your time, I'm not going to go through the plan demo. I will point you instead to the repository, to the source repository, and this presentation will be shared hopefully, and the link you can find in the article on the website. But what I will show you briefly is the repository itself. Let me just change the presentation view, and I will go to the repository. Here you will be able to see, and there is a step-by-step instruction how you can deploy this. You will find sorry, just a second, for the AWS demo. This is actually, there is something else that I actually wanted to share with you. Sorry about this. It's actually sls.guru website with this article. So I will point you there, and check the blog for the establishing trust between services with certificates. Here you will find the AWS demo. You will find step-by-step instructions. You saw this screenshot during the presentation. You will see step-by-step instruction what to do. So you will need to put some environment variables. The project itself is OpenTofu, and which is open source Terraform. It will allow you to deploy service on both ends if you're interested. Just pay attention that there are a lot of paid and expensive services, so it will cost you some money if you deploy. Don't forget to clean up after yourself and remove the resources. And this is from the CLI how you will how you can create certificates. So everything here is explained in depth, step by step, and you can clone this repository. The link is in the article, and try to deploy by yourself. Also, that's not all. You will find the Google Cloud demo, and you will also find, as a bonus, you will find Azure demo to test what we talked about in this presentation. You will be able also to use the private DNS, so you can set whatever you want, but you will find you can override settings. You will find setup for the private DNS as a secrets.guru, which is imaginary domain that is that we use for the demo purposes. So with that, I am not going to take any more of your time. So I hope that I was able to explain what is a TLS, mTLS, these cryptography things, and how to use it. So if you have any questions, I will be happy to answer them right now. So I was not following the... Okay, I'm reading the comments. Okay, TLS also used for some UDP as well, and DTLS. That's good point. Thanks about that. So there are some useful information in the chat, and I will refer to this comment also. Okay, so what man in the middle attack, with man in the middle attack, it happens before encryption even begins during the key exchange. How often do attackers actually exploit this window, and what's the most common failure point? Well, the thing with the man in the middle attack, any other attack. So attacker will try to exploit anything that you have. So they will look for your any vulnerability they can found. And if the connection is not secure, if this handshake and TLS is messed up and they see the opportunity, they will use it. I mean, how often they will exploit and how successful they will be. Well, it really depends. I mean, it depends of the how attacker is interested in your data, how skillful the attacker is. But if we are working in a very sensitive environment with very sensitive data, where the personal data is involved, where they can gain where they can gain something for themselves, and they have a interest to do so, you better be protected. I mean, they will do everything to get to your wallet, to your credit card, to your money, to whatever they can get from that. I hope that answers the question. I mean, it's a generic answer, but it's really hard. It's really hard to say in which way they will exploit that. So I mentioned one way, for example. Let's say if you trust your network, so you have your VPC inside of AWS, and it's a safe network. It is isolated. It is private. It doesn't have internet connection, and you trust that network. Fine. But if the network gets compromised, so some attacker gets access to your account and get access to the network, then they can probably exploit your traffic between the services. So these are all theoretical things that could happen, but you should try to protect and make sure that they don't happen. So about the regular. I mean, if you believe that your keys are being compromised, the best way is to rotate them. I mean, you cannot easily be aware. I mean, you need to observe your whole system. You need to be aware of what is happening, and if there are, and you need to monitor your traffic. If there are suspicious traffic in your network, and somebody or something accessing things that they shouldn't, or trying to access the things, then you should rotate the keys, because if you have permanent key, and let it be like that, and you never rotate, it's same like the passwords. Old passwords become bigger and bigger risk over the time. Same goes with the keys and the certificates. If you are not rotate them over the time, they can become compromised. So to audit your setup, you should probably go and check your when the key has been issued, what is the expiry time, and if you think, or if there are suspicions and you are suspicious that somebody got access, or that keys are compromised, even if they are not, but it comes to your mind, then just rotate the keys. That's the best way. That's the best way to protect yourself. Don't wait and see, is that really true, because it may be late. Okay, I think we don't have any more questions for now. And thank you very much for these. These were really great one that provides some additional context, and also thanks for the comments about the UDP, DTLS, and for the user some random string. So thank you very much for that. And yeah, with this, I will close up this webinar. In case you have any additional questions, ask on our sls.guru official Twitter, or ask on LinkedIn, and we'll try to answer them whenever we can. So thank you very much for your attention, and thanks for attending this webinar. Hope you liked it. Have a great day.